Hi, I'm Eli Sadovnik, and my project was on designing a successful robotic arm in the context of the first robotics competition. Um, and so the first question is obviously what is FIRST and what does that have to do with robotics and robotic arm? FIRST stands for Inspiration of Science and Technology. It's an organization that holds an annual robotics competition called the First Robotics Competition. The Newton North and Newton South jointly have the team, the Robots, of which I've been a part of since I was a freshman. Every year, FIRST gives us a game that we basically have to have the robot play. The first year it was soccer. Last year it was basketball. This year it was frisbee. 2 years ago it was completely different. You had to take tubes and place them on pegs, like you see here. And so you have a 6-week period within which to design and build the robot, and then you have to go and compete with it. And so I'd say about half the games that FIRST puts out require the use of a robotic arm, and we've never really done it well on the light rod, so I wanted to sort of research how we can do it better. As you can see, here's a very professional looking robotic arm. I've never seen it in action though, so I can't speak to its efficacy. So really my bottom question was what makes a successful robotic arm? And I boiled it down to the two most important things, which are the ease of use for the driver and its robustness. And those really came out of my experience 2 years ago when we tried to build 2 robotic arms on the robot and neither of them worked. The first one was the one that I built. Did not work at all. It was supposed to, you can see it on the left here. You had to take a mini-bot that's within the confines of your robot to begin with, and then at the end of the game you were supposed to put it onto a pole, and the mini-bot has to climb up the pole and hit a button on the top that's like, I think, 10 feet high. And so that was fine. I built the mini-bot. That wasn't the real challenge there, I think. I think the real challenge there was being able to engineer a mechanism to take the mini-bot and put it on the actual pole. I designed and built it, and it was incredibly difficult for the driver to use. He had to line the robot up within, I'd say, half an inch of clearance, swing out the arm, and then he had to drive maybe an inch to get the mini-bot in the right position and then let go, which is very difficult because these robots tend to have very jerky movements. And so, unfortunately, the robot never scored by that method. The other arm that we had on our robot that year was the one to grab the tubes and place them on the pegs. That didn't work for the other reason. It wasn't robust. What happened was there was a telescoping system in the middle. As you can see, that little box at the top rode up and down on the elevator. And that was fine, but the claw that was holding the tube was supported only by a 1-inch thick piece of aluminum box, which was not sturdy enough. It would flap around a lot during the competition. And additionally, the backboard that held the tube in place was too flimsy. We made it out of 1/8-inch aluminum instead of, probably should have gone 1/4-inch aluminum. And so it actually got bent out of shape at one point, really badly. We had to engineer a new one, and it didn't work. So those are the 2 biggest and most important factors that need to come into the design and engineering of a robotic arm. Now, how do you do that is the next question that comes up, and I hope I've answered that throughout the course of my SYP through various design methods that I've constructed. The first one is to have a piston-actuated joint near the base of the robot. This serves to put the arm into either one of 2 positions, either vertical or at some angle. That other angle allows you to more easily gain access to the floor, where you'll most likely be picking up tubes and other game pieces to place them elsewhere. And then it'll be able to snap back to vertical when you want to place it on a peg or something like that. The reason why a piston is so good for this job is because A, of its binary movement, and B, of its large amount of force. A piston is a pneumatic system. What happens is a compressor basically just compresses air into a bunch of air tanks that you have on the robot. And because you're able to spend so much time building up that pressure, you're able to exert much more force than you could with a motor on this type of joint. So a piston is able to withstand the amount of torquing forces that are exerted by the gravity of the rest of the arm on the other side, whereas a regular motor really couldn't. And the other reason, the binary motion of the piston, the arm really needs to only be put in two positions, one for picking up off the ground, one for placing it elsewhere. Arms and first generally have binary roles. They pick up and they place down, or they swing out and they place them in the bottom of the pole, or something like that. So it doesn't need any more continuous motion like that would be given of a motor or a winch or something like that. So a piston is well suited for this. It makes it easier for the driver to use. It does make it a little bit less robust because it adds another joint to the robot that could destabilize it. But since it's so close to its base, that's really, I don't think, significant. Okay, so that was my first design. My second design is a 3-stage telescoping arm actuated by a lead screw. A lead screw is a type of threaded rod where you have a nut on it, and you spin the lead screw and the nut will travel along the threaded rod linearly. So it's a way of turning rotational motion into linear motion, which is a big theme in my paper, not here, because linear motion is really easy to look at. Oh, it's just in line, we just pick up, rather than having to sort of gauge some sort of circular arc that would be given by the motion of a motor or something like that. So methods of turning linear rotational motion into linear motion are very important. Lead screw is one of them. So here what happens is, I can see that the lines that I drew for the table, we can copy over from Mac to PC. But the point is that there's one stage that just sits there, just holds everything in place. And then the next stage is actually attached to the lead screw through the nut. So when you turn the lead screw, the second stage moves out. And then what happens is, if you can see, there's some very faintly drawn dashed lines there. And what they do is, as you push the second stage out, the third stage out will be pulled along by the red cable. But in turn, because the red cable has to go through the hole, it's going to push it out twice as fast as the second stage, which makes you have to actually exert twice as much force, but it gives you twice as much speed, which is actually great because the lead screw is notorious for its slow motion, high force motion. So this is a way of sort of scaling that back and getting more normal motion that would be applicable for normal weights and normal speeds. So it also extends to 3 times normal length, whereas most telescoping arms within first only extend to 2 times because they're only 2 stages. So. Now another design method that I didn't come up with this one, but it's good. It's using a worm gear. A worm gear is a special type of gear where you have a screw and then you have a gear. The screw is called the worm, the gear is called the worm gear. If you spin the screw, then the gear moves along with it. So it's a way of really just scaling up torque and scaling down the speed of the whatever you're actuating. But the really cool thing about worm gears, and this is actually also true of the lead screws, is that they're self-locking. If you turn the worm, it turns the gear, but if you turn the gear, you actually can't turn the gear. The worm locks in place because now you're battling the normal force from the threads of the worm if you're trying to turn the actual gear. And that's the same line of reasoning goes for the lead screw as well. So the telescoping arm in the previous slide is also self-locking, which is really helpful for if you want to just sort of have the arm stay in a sort of precarious position. It can just sit there instead of having to have some sort of dynamic force actuated on it by a motor, which is really helpful. Doesn't show up. An important part of designing some sort of mechanical system is picking a motor and gearbox to go along with it. Now, a motor is one of the problems with the ARM 2 years ago was that we actually picked a motor that wasn't powerful enough to really actuate it well. So I wanted to research how you can pick a better motor, how you can pick a motor that's more suited to the job that it needs to do. And so what I learned from my research was that motors have a certain amount of juice in them. I'm not going to call it power since that's technically another quantity, but they have a certain amount of juice in them, and they put all of the juice that they need to towards actuating a certain joint or lead screw or whatever. There's a certain amount of torque required there. And it puts the rest of it towards making it go as quickly as possible. And so that's all well and good. But then what you do is when you gear it, you scale up the you scale down the free speed by a factor of R or whatever the gear ratio is, and you scale up the torque. And so this can all be mathematically simulated, and if you actually make a plot of the maximum of the speed versus the gear ratio, you'll get a curve that actually has a single maximum point. It's a relatively trivial calculus problem to then figure out the maximum free speed and the best gear ratio possible for that motor and that given torque. And so that is one of the methods that I use to decide what motors to use, because then I can see, oh, with this motor and this required torque, I'll be able to actuate at this speed, and that's enough. Or, oh, it's too weird of a gear ratio for me to be able to effectively use, or it gave me more, it informed my decision when I was trying to figure out what motor to use. And then my last design method was to have sort of a hybrid end effector. End effectors, which are the things that actually do whatever the arm is designed to do in a first competition. The end effector is almost always, some sort of variation on a C-shaped grabber. There's usually two types. There's the one up on the top left, which is where you have the C, and on either side of the C, you have sort of conveyor belts that pull in the object, and then you move it around, and then you place it wherever you want. And that's great. And then you have the one on the top right, where you have the C, and that actually clamps down on the object as you go down to grab it, and then you move it around, and then you place it wherever. These are great, and there's a reason why they're so common. But one problem with the what I call the active type, the one with the conveyor belt that actively pulls in the object, is that it's very prone. It's not very prone. It's relatively prone to having the object fall out or move around while you're moving the arm around to maneuver it into position. Whereas the other one gives it much more stability because you're able to grab it much easier. However, the other one, you have to sort of get leverage on it to begin with, so it's hard to grab in the first place. And so my design, which you can see at the bottom, is one where you have that red piece of metal that just sort of flips open and closed, and you have a conveyor belt that goes and grabs it so you can get at it easily. And then you just sort of flip it down so you can easily move it around and not have it fall out as you're trying to place it, which is, I think, one of the leading causes